Okay, good to everyone. I will discuss the major gas laws using the Phet simulation for gas laws. Okay, in the gas laws, the gas laws describes the relationship among the properties of gases. We have the pressure, the volume, the temperature, and the amount of gas. This law help us predict how gases behave when conditions change. So I will discuss first, or I will introduce first the parts of this Phet simulation. You can see the pressure here in this symbol, the pressure meter here. The unit for pressure here is atmosphere. And you can see the temperature, or the simulation for temperature is here, the thermometer simulation above. And the unit for the temperature in this simulation is Kelvin. And you can change the temperature by turning this bottom up. We can increase the temperature by turning this bottom up, and you can decrease the temperature by turning this bottom down. And when you want to increase the particles of gases, you can pump gas inside this container or rectangular container using this simulated air pump. You can use heavy particles as represented by blue dots and light particles as represented by red dots. And you can also change the volume by moving this icon here. Okay, just like that. And if you want to control what variable or what property should be constant, you can click on what particle you want to be constant. For example, I want to hold constant the volume, so I can select volume. Now let's begin with the Boyle's law. If you say Boyle's law states that the volume of the gas is inversely proportional. The volume of the gas is inversely proportional to its pressure when the temperature and amount of gas are kept constant. Okay, if you say if you say Boyle's law, the volume, this is the relationship between the volume and the pressure. The relationship according to the Boyle's law, the relationship of the volume and the pressure is inversely proportional when the temperature is hold constant and the amount of gas hold constant. Okay, in this simulation, how can I hold the temperature constant? I can click the temperature here. And how can I hold the amount of gas constant? I can hold the amount of gas constant by not adding more gas particles. So we can hold the temperature and the amount of gas constants. Now let us see the relationship, or the inverse relationship of the volume and the pressure. If I change the volume, what happens to the pressure? And if I change the pressure, what happens to the volume? But in our case, we can change, in this simulation, you can change the volume. So let us see what happens to the pressure. Okay, if you observe, when I change the volume, when I increase the volume, or the amount of space occupied by the gas, the pressure, when I increase the volume, the pressure decreases. When I decrease the volume, the pressure increases. Because in Boyle's law, pressure and volume changes, the temperature remain constant. The temperature remain constant. The temperature does not change, and the amount of gas remain constant. So if I change the volume, if I increase the volume, the pressure decreases. If I decrease the volume, the pressure increases. Why? Because if you can see, if you say pressure, this is the amount of or the force exerted by the gas particles to the walls of the container. They exert force by colliding to the walls of the container. If the space occupied of the gas are limited, just like for example, we decrease the volume, there are more chances of collision between the walls of the container with the particles of the gases, so the pressure increases. So that is the Boyle's law. I repeat, Boyle's law states that the volume of the gas is inversely proportional to the pressure. So when the volume increases, the pressure decreases. When the volume decreases, the pressure increases. Okay, next law is the Charles law. Charles' law states that the volume of a gas is directly proportional to the absolute temperature. So in the Charles' law, we will observe the relationship between the volume of the gas, or the space occupied by the gas particles, and the absolute temperature. So we will observe the relationship between the temperature, and the volume of the gas. And according to Charles' law, the relationship between the volume of the gas and the temperature is directly proportional when the pressure and amount of gas are kept constant. Okay, let us first hold constant the pressure and let us see what happens to the volume. Because Charles' law indicates that the relationship of the volume and the pressure, the volume and the temperature. So let us hold constant the pressure and let us change the temperature. So let us see what will happen to the volume if I increase or decrease the temperature. Since Charles' law states that directly the relationship between the volume and the temperature is directly proportional. Okay, if I increase the temperature, you can see that the amount occupied by the gas, or the space occupied by the gas, or the volume of the gas increases. If I decrease the temperature, the volume of the gas decreases. Since, according to Charles' law, the volume of the gas and the temperature are directly proportional. Okay, I repeat, if I increase the temperature, the volume of the gas decreases. If I increase the temperature, the volume of the gas increases. On the other hand, if I decrease the temperature, the volume of the gas decreases. So the relationship between the volume of the gas and the temperature is directly proportional. Okay, let us hold constant again the pressure and let us see what will happen to the temperature of the gas if I increase or decrease the volume, or if I change the volume, if I made changes with the volume. Okay, if I increase the volume, the temperature increases. As you can see, from 300 Kelvin to 374 Kelvin. If I decrease the volume, the temperature decreases. From 374, if you observe, from 374 Kelvin, it goes down to 219 Kelvin. So this simulation shows that, or it shows the relationship of the Charles law, the volume, and the temperature. If you increase the volume, the temperature increases. If you decrease the volume, the temperature decreases. So the relationship between the volume and the pressure and the temperature are directly proportional. They are directly proportional. When the temperature increases, volume increases. As the temperature decreases, volume decreases. Okay, the third gas law is the Gay-Lussac's law. The Gay-Lussac's law states that in this law, we we'll observe the relationship between the pressure. So you will observe the relationship between the pressure and the temperature. Since Gay-Lussac's law states that the temperature of a gas is directly proportional to its absolute temperature when the volume and the amount of gas are kept constant. Okay, how can I hold the volume constant and amount of gas constant? I can hold the volume constant by clicking the volume tab here, and I can hold the amount of gas constant by not adding more particles of gases inside the container. So let us see what will happen if what will happen to the temperature if I decrease the pressure, or what will happen to the temperature if I increase the pressure, and vice versa. So if I increase the temperature, if I increase the temperature, if I increase the temperature, the pressure increases. Okay, observe clearly what happened to the simulation. If I decrease the temperature, the pressure decreases. Why? Why? Okay, if you observe, when I increase the temperature of the gas particles, the gas particles move faster and faster. They move faster and faster. When they move faster and faster, there are more chances of collision to the walls of the container. So the pressure increases. If I decrease the temperature, the gas particles will move slowly. And when they move slowly, there are less chances of collisions to the walls of the container. So the relationship between between the temperature and the pressure is directly proportional. If as the temperature increases, gas particles move faster and collide more frequently with the container walls, increasing the pressure. In Gay-Lussac's law, I repeat, this is the relationship between the pressure and temperature when volume and amount of gas are remain constant. Okay, the next law we have the combined gas law. If you say the combined gas law, this is the combination of the three laws. The combination of the Boyle's law, Charles' law, and Gay-Lussac's law into a single equation. So it describes the relationship among pressure, volume, and temperature when the amount of gas is remain constant. So how can I hold the amount of gas constant? I will not add particles of gases here to hold the amount of gas constant. For example, if a gas is compressed and heated simultaneously, the combined gas law can be used to determine the final conditions of the gas. Okay, in the combined gas law, you can observe the relationship of the three properties. The relationship of the pressure, the temperature, and the volume in the combined gas law. For example, if I increase the temperature, the pressure increases. Okay, if I increase the temperature, the pressure increases and the volume increases. Why? Because if I increase the temperature, the gas particles move faster and faster. So when they move faster, there are more chances of collision to the walls of the container. And why the volume increases? Since they move faster and faster, they need more space. They expand, they move freely to all directions. So the more space they need, the volume increases. Okay, let us see. Again, what will happen if I decrease the volume? If you decrease the volume, the pressure also increases. Since the amount of space are less, the particles of the container or the particles of the gases collide more often with one another. So those are the combined gas law. If you say combined gas law, this is the relationship between the pressure, volume, and temperature. Next is the Avogadro's law. If you say Avogadro's law, this is the relationship. It states that the volume of a gas is directly proportional to the number of moles of gas when temperature and pressure are held constant. If I held the temperature and pressure constant, what will happen to the volume and the number of moles? Okay, if you increase the number of moles or the particles of gases in the container, what will happen to the volume? Okay, kindly observe. When I increase the number of particles inside the container, I pump air inside the container. So when I pump air inside the container, I increase the number of particles or the amount of gas inside the container. When I increase the amount of gas inside the container, the volume increases. If you observe, the container expand, so which means the volume increases. Now, if I decrease the if I increase the amount of gas here, the volume increases. Since the relationship of the volume and the amount of gas is directly proportional. When this means that adding more gas particles increases the volume, while removing gas particles decreases the volume. So in Avogadro's law, I repeat, this is the relationship between the volume and the amount of gas when the temperature and the pressure remain constant. Finally, we have the ideal gas law. If you say ideal gas law, it combines all the four properties of gas. We have the pressure, the volume, the temperature, and the amount of gas into one equation. So the ideal gas is used to solve problems when several gas variables are involved, and it's applicable to gases that behave ideally. For example, if we know the pressure, the volume, and the temperature of a gas, we can determine the number of moles or the amount of gas present in the container. So to summarize, Boyle's law, pressure, it represents the relationship between the pressure and the volume are inversely related. Charles' law, volume and temperature are directly related. Gay-Lussac's law, pressure and temperature are directly related. Combined gas law relates the pressure, volume, and temperature together. Avogadro's law, volume and the amount of gas are directly related. Ideal gas law combines pressure, volume, temperature, and the amount of gas into one equation. So understanding these gas laws help us explain many things that happens every day, from inflating balloons, using syringes, to understanding how gas behave in weather system and industrial process.